So, hello everybody. Let's welcome Philippe with his talk, ReVault, compromised by your secure SoC about the Dell security chip and its compromises. Give him a warm applause.
Thank you. Can you hear me? Yeah. Okay. So today I'm going to talk about ReVault and how you can get compromised by your secure system on chip. So hi, I'm Philippe Laulheret. I'm a senior advanced researcher at Cisco Talos, and I focus on Windows and embedded systems and stuff like that. And if you're not familiar, what my team does is basically we find vulnerabilities in third-party software. We report that to the vendors, they fix it, and then we release that research, publicly, on blogs, on talks, and so on. So what to expect from today's presentation? So we have 45 minutes, and I'm going to go over some of the bugs that we reported to Dell and Broadcom earlier this year that lead to a full compromise of something called Control Vault. And we're going to see what it is in a sec. So that's one of those Dell laptops, and you can see here you have fingerprint reader, you have an NFC card reader, and here you have on the side you have a smart card reader, and all are those peripherals that will connect into that Control Vault thing. On the device manager, you can see it as well. This is this mystery stuff that's in your system. You don't quite know what it is. And if you open the laptop, remove the battery, you can see it here. That's the Control Vault board. It connects here to the motherboard, and you can see a bunch of stuff plugged into it, and there's a little chip here sticking out. So at this point, you should be okay, what is Control Vault? So technically, it's Control Vault 3. And it can be found in over 100 different models of Dell laptops. So the business type, so Latitude and Precisions, which is roughly tens of millions of devices. And the board is here. It's yay big. It's not as usual it looks on this slide. It's a mix of software and firmware and hardware. You have Windows APIs or Linux APIs. The chip here, it's a Broadcom BCM58202, which is an ARM chip that runs a real-time OS that we're going to look at. And technically, it offers a secure storage of secrets. So the chip here is a flash module that's encrypted. And it's also called the Unified Secure Hub, which connects the fingerprint reader, the smart card reader, the NFC reader, on those ports here. And so it's Control Vault 3. There is Control Vault 3 Plus, which is on the newer Dell Pro models. And before that, you also had Control Vault 1 and 2. The original Control Vault was 2010 or so. Control Vault 3 that we're talking about today is 2019. But that being said, some of the vulns I found in Control Vault 3 appears to be already present in Control Vault 1, so some of those bugs were there for 15 years. And there is no documentation, so we're going to have to do some work, but that's the fun part. Step one, we can try to Google all the things, and one of the useful finds is that link here, which is just the Linux host APIs. So basically, if you want to have that working on your Linux for a long time, that wasn't possible, but now you have that, which is official by Broadcom. But the fun thing about that is it's compiled with debug symbols. So if you import that in IDA, it will give you all the function names for the host APIs, but also data structures enums and stuff, and that's extremely useful for reversing because all of that is being sent to the firmware and used as is, so really useful. And then if you Google more, you might find that stuff, which is some certification for the crypto module inside the system on chip. And doesn't give you that much information, but gives an idea of how it works. And also it spells out some of the acronyms used in the system. For instance, SBI here would stand for Secure Boot Image, and it's part of the security system of the thing, which is cool to know, but it's going to be useful eventually. And it could be why do you want to target that? Beyond the fact there's tens of millions of devices that have it. The beginning of that project was a little more humble. I was, looking for a next target, and I was looking at stuff running on the system I had. And here, something caught my attention. You have a bunch of system services, and ASLR is disabled. So, ASLR, address space layers randomization, which is meant to make harder stuff to exploit harder, and it should be everywhere, but it was missing here. And likewise, some of the DLLs being loaded by the services were also missing the SLR. So those are the Broadcom stuff that talk with Control Vault. So I got really excited. I started yelling through the window of my car, And then I move on, and it's like, let's dig deeper, let's understand how things work, And so like first step is like just looking at the files, from the installer. And there's so much stuff. You have a driver for the USB, a driver for the fingerprint reader, smart card, NFC, like tons of stuff. There's also a bunch of Windows services and associated DLLs. And then there's a firmware folder, which got me like pretty excited. And among that, there is the SBI stuff, so the secure boot image. And that's nice, it's in clear text. You can see strings in it, or you can import it in IDA, if you're curious. And then there's one called like Citadel, and that one, unfortunately, is encrypted. So I was like, oh, I want to know what's inside, So it's like, it's going to be like kind of our task is figuring out what that is. But there's the main application firmware that runs like all the stuff, control vault. But before we go too far, like let's give a system architecture ID. So here's the firmware. Start with the boot ROM, that start the SBI, that start the application firmware. On that side, you have like the host. So in our case, mostly Windows. Talks over USB to the system. Here you have like the USB driver. Control vault APIs that are being used for like various services and stuff. And on the other side, you have like the hardware that's like the fingerprint reader and so on. They all talk over like different buses to the device. Cool. So now, like to talk with the firmware, like the way it works is the USB driver on Windows is going to create like a device file, and userland can open that device and send device I/O control to it. Eventually, that will lead to like the driver sending USB packet to the firmware. And that's super tedious, to do. So the Broadcom engineers like made like a high-level, API DLL that exports like tons of functions called like CV functions, like CV open, CV close, create object, get object, for like secure storage of stuff. And I think there's like 150 of them, so that's a lot, and they're like a big attack surface. And most of them requires a session that you get from like CV open. And on the firmware side, you're going to have like a handler function called like CV manager or CV manager SBI that receives those CV commands and then dispatch them to whatever function. And that's obviously like a big attack surface that we want to look at. But before that, just to give an example of how to talk with the firmware, like for real, what you can do in Python is like you can open the Broadcom DLL that's like exporting all those functions, and then just do a bit of C-types, Python stuff to just define, like the expected parameters of the function that you can get from the symbols you got from, 10 slides ago. And then you just like call the function. And in that case, I'm calling the get USH version, which returns the version string of your firmware. So with like 20 lines of Python, you can immediately communicate with the device that's in your machine that before that you didn't know existed. So it's pretty neat. Okay, so now we know how to talk with the thing, but what's the threat? What do we see like spicy? There's like 4 different main areas of interest. I think the first is like the SBI and the application firmware. So they receive like USB commands, they receive like CV commands, and then they have like even more stuff like to deal with like those Broadcom services that it's even more complicated. So that's one big chunk. Then you have like how the secure boot process and how like the firmware is being updated and also like signed to make sure you don't run like arbitrary stuff on that device. So that would be interesting to see how they do that. And then you have like all those Windows services on the host side. Like originally I was like just wanted to target the USB driver, looking for easy elevation of privilege or something. But then you have like those Broadcom services, and all of that stuff is of interest. And the last one, not going to cover that today, but I wanted to highlight it, is the hardware side. Because what if, like a malicious fingerprint reader was talking with the firmware and would, try to compromise that? Or the other side of that, like what if a malicious firmware would try to compromise the fingerprint reader? And those are really cool questions, but answering them would like 10x the scope of this project. So didn't do it, but maybe if someone is interested, that's a worthy thing to explore. And just to double down on the secure boot side of things, a kind of vague diagram for now of how it works is like you have the boot ROM that's going to verify cryptographically like the SBI. And the SBI is going to use this structure called the secure code descriptor that contains some keys and stuff to start the application firmware, like the Citadel stuff that we want to look at. And all of that can be updated and should be verified, and we'll dig into like how that works. So that's kind of like the general idea. Now, what are the mitigations? Like this, we want to do some exploitation eventually, so what's going to be hard for us? The Broadcom services that we've seen no SLR, so it's good for us. There is DEP, so data execution prevention. So you cannot just jump on the stack and execute stuff. It's not the 90s anymore. And for like stack cookies, like stuff that would make exploiting Stack Overflow harder. Well, that's surprising. Sometimes we have a stack cookie, sometimes we don't. So it's like, I don't know, it's like some weird compiler flags or optimization. So it's like 50-50. And on firmware side, one really cool feature is that it does encrypted execution in place. So the chip, the flash I was pointing at, contains the firmware that's encrypted and that can be executed that way. And then also there's like the secure boot. We'll see how secure that is. But then there is no SLR, no stack cookie. So if you have a Stack Overflow in the firmware, like you pretty much can get code execution. DEP is a maybe. If you try to execute the stack, it will crash. But there is like read-write execute regions like mapped in memory. So if you put your shellcode in there, like it's done. Like you can do whatever you want. So on the firmware side, not the best mitigations. Okay, so now that we have an ID, well, it's time to reverse stuff. So remember, like the situation we had was the SBI was clear text, but the main stuff was encrypted. So we want to kind of decrypt it, hopefully. So how do we do that? Like usually the trick is to like search for strings and see if it mentions like decryption, and indeed it does. It's like pretty sad. It's talk about failure, but that failure is our success because we find where the decryption happens. And the way it works is it's like a 3-step process initiated by the host, so like in our case Windows, and we'll send to the firmware like that field upgrade start command, and it provides an encrypted header for the firmware. And if there is no key present, it's going to use hard-coded default, which is cool for us because we know we don't have keys, so hopefully this works. And then when it gets that, it's going to generate new keys used to securely store that firmware onto the flash for the execution in place and stuff. And then the host is going to call the upgrade update command and basically send blobs of encrypted firmware that gets decrypted, and stored on the flash. And it's using a custom IV for that. We'll see that in a sec. And finally, like when it's done, it calls upgrade complete. The system does like a firmware, like a full verification of the signature. And if it's all good, it commits what remains to the flash, and then we're done. In practice, that looks like that. We can see here during the upgrade start. So that's like screenshot from the SBI, the secure boot image. You can see like it's loading some default keys and default IV. I'm not putting them on the slides so that I don't get in trouble with like Dell and Broadcom. But yeah, and then it calls the decrypt function. The decrypt function here like takes the IV, and inside the decrypt function you can see like it takes the key here. And unfortunately, it's just a wrapper on the cryptography module of the chip, so we don't really know why is the decryption function. But from the certification we were looking at earlier, we can have an idea of what's possible, and we can just try different algorithm until it works. So the answer was it's a AES-CBC, and it's indeed using the default key and IV. Sometimes there are multiple SBIs and may have different keys, so if you don't unlucky, you pick the wrong one and it doesn't work, but the main one does work. And when you decrypt it, it looks like that. Like it's like you can see some pattern. It's not like just totally random data. So it's like you decrypted successfully, even if you don't really know what it means. And here's like the actual like AES key, and this one I obfuscated. And the one thing is like the STDs, like multiple versions of them, and some is like little Indian, some are like big Indian, and it's like confusing. Anyway, so now that we figured out how to reverse, how to decrypt the header, we want to decrypt the actual firmware. And for that, we look at the upgrade update command, which, basically it's a loop that's going to decrypt a chunk of it. And as I pointed out, the one gotcha is it's using a custom IV command to, like the initialization vector for the crypto stuff. And basically, that's what the command looks like. So what you can do is just like copy paste that into Visual Studio or like re-implement it in Python, and it gives you the value. And basically, it's just using the memory address where the blob of code is meant to be mapped at as the data somewhere, the address. And that's its stuff. You run it on the whole firmware, and eventually you're good, you decrypt it successfully, and you get the strings, and you can see like Broadcom, a bunch of stuff. So, with like a bit of like effort, you get decrypt the firmware, and now we can actually start doing the interesting stuff, which is like looking for variants. And so I was saying, like all those like CV commands, which are kind of like the most obvious attack surface, they most of them need like a session. And for that, you call the CV open command. And so in the firmware, that's what it looks like when you call the CV open, cut some stuff, but allocate a bunch of data. And then it's writing like a session tag, the letter like SESS, in the blob of data that's been allocated. And then it returns a handle, back to the host. But the handle is really just the pointer of the session, which is already quite curious because immediately you're leaking, addresses from the heap back to the host. It's a little problematic, but it's not the end of the world. But curious choice. But then like we good people. So when we open something, we also want to close it, right? It's legitimate. And so to close the session, you send the handle, which is the pointer to the session. And the firmware is going to validate the session. And to do that, it just makes sure that the pointer you just sent is in the proper range, in the heap. Like it's a fairly small heap. And then it looks for the session tag, and then there's like a few extra checks, but they don't matter. And if it finds the tag and it's the right address, it's good. The session is validated. It erases the tag and free the memory. And now, like if you like to play CTF, you might be like, well, my hacker like sends like tingles a little because really the only check is like if the address you send says like SESS at the beginning. So we might have an arbitrary free on the heap. That's if we can place arbitrary data. We're like, So is it possible? Yes, it is. You have the CV create object commands that put objects on the heap. And you provide arbitrary data, arbitrary size. So yeah, you can just, from that, place any data you want on the heap, including SESS as a tag. That being said, you don't control all the metadata of those objects. So it's not like, you're not whole powerful in that regard. And also, the handle you get from that function is actually a random number and not the address of the object. So while you can place data on the heap, you don't quite know where it is. But that's not an issue because you can take any other function, for instance, like cv_get_random, which is meant to return random data from the crypto module. And the first thing it does is validate the session. And depending on if the session is good or not, it will return different error codes. And so what you can do is just like scan the whole heap range, because it's a small heap, and ask, is it a valid session or not? And there is no side effect in doing that. So with that, we basically have like a session oracle that lets you locate the blob in the fake session that you would have put on the heap. So with all of that, we have create object that lets you place data on the heap. There's also, I didn't show them, but get object and set object that lets you read and write your object, normal. With get random, you can locate your object, and with close, you can free the thing that would look like a session. And with all of that, we have an arbitrary free on the CV heap, which is nice, And now you'd be like, okay, is it time for like heap exploitation? That's me, when I have to do that. Like I like CTF, but the heap ones are like always like giving me headache. So instead, I was like, okay, maybe let's find more bugs. That's also my job to find bugs. So maybe I can just do a little more of that and put a pin on that one. And let me introduce a different function. It's called like secure bioidentify. Even if it doesn't have CV in the name, it's also reachable with one of those CV commands, from like any user on Windows. And one of the things it takes is a object handle. And what it does, it loads the object, and then somehow it memcopy one of the field of the object into this like data2 buffer, and this data2 buffer is just some random stack variable of size like 32. So here I was like, do I already have like a Stack Overflow with my like object value? Because you can see here, it's using the property of the object. So unfortunately, fortunately, I don't know, we need to control that value. And it turns like during object creation, with CV create object and stuff, you cannot do that. I think there might be a legitimate way of controlling that value anyway. So we also reported that as a problem. But we really don't care because, 3 slides ago, we had a heap corruption primitive that let us tamper with stuff. So we can tamper with a legitimate looking like object that was created and just change the size of that field to make it like malicious. So to do that, what we can do is allocate, like a malicious object that looks like a session. For diagramming purposes, like that would be the object. The purple side is like data we can control and modify. The blue is like the metadata we don't control. And here we put the session tag already in it. So what we can do is free that object, using CV close, and then allocate a smaller object. And the way the memory allocation works is just going to put it like in the hole we just poked in the big object. It's like the two objects are being overlapped. And we can see here like the purple side, also overlap with the blue side, meaning that by modifying data in the big object, we really can modify metadata of the smaller object. And so we can tamper with the small object, put malicious data in it, and then we use that small object to feed into secure bioidentify, and boom, we trigger like the Stack Overflow with our malicious like object value. And with that, because there is no security mitigation, we can execute code now. So that's nice, and we have code execution on the firmware. But what do we want to do, So there's like two ideas that are kind of cool. One is we can run whatever code we want, and then return the data, the output of the malicious code we run, back to user land on the host. And to do that, we could run an exploit, and then make it write data inside that large object that we control. And then we can use the get object primitive, to read that data back to us. And this way, we can dump the RAM, we can dump the boot ROM of the system as well. It's pretty fun. But then there's like another like spicy command called SOTP read key, which is used to retrieve key material that are stored in the fuse of the chip. So you're not supposed to be able to call that, but that's a function in the firmware. And with that, you leak keys, which sounds like a good thing to do. So that was like one idea. Like the other that I'm not going to cover further like today is you can also patch function pointers that are like in writable section of the firmware, and with that you can kind of like backdoor like hook certain like legitimate functions. And the idea with doing that would be to be like baby steps towards like firmware modification, because you can hook certain functions, but you're kind of limited. And we're not going to talk about that more, just because we'll have like a better approach for doing that. So suspense. Anyway, the first demo is like we're going to see how like the dumping the key works. And so let's see. So what is going to happen is like I'm going to create that fake session and then call the SOTP key. So the first step is like I'm using the session oracle to locate existing session, because it's a laptop that has a fingerprint reader and like is being used, Then we forge the session and we free it. We exploit the secure bioidentify, call the SOTP read key, and actually we do that twice. And then boom, we leaked two keys, the HMAC key of the device and the AES key of that device. And those are like my device, so it's like fine to put them on the screen because that's just one, it's per device keys. That's cool, but now you should be like keys, like what are those keys, So there is like a bunch of key material in that firmware. One is like the one stored in the fuse, so you have like 7 key slots, and these two are like AES and HMAC, and those are like for the secure storage on the flash. So and it's like both like encrypted and kind of authenticated. And something else that's like stored with that is the secure code descriptor that I pointed out, in the boot process earlier in the slides. The SCD, so the secure code descriptor, also contains key material, including an RSA key that's used for like the firmware verification, and the AES and HMAC key that are used for encrypting the firmware, and that's being used for the execution in place. So those are like different key material. And finally, there is also the hard-coded default keys, the one we used earlier, to decrypt the thing in the first place. And those are actually being used when the SCD is missing. And you could be like, okay, how do you lose your SCD? What happened to it? Why is it not there? And it turns out there is this lovely file called like clear_scd.bin. And I don't know if you guys can see, but it's just like 012f, a bunch of times. And that's actually used for legitimate purpose during firmware update to do reboot in the SBI mode. So the updater is just going to call a function called cv_flash_update that writes to the flash and overwrite the legitimate SCD with junk. And when you try to reboot, like the SBI is going to be like, I don't know what's going on, and it's going to stop and wait for like proper firmware update. So that's somehow the mechanism they choose to implement for rebooting in SBI mode, which is a little contrived. And the crazy thing is we have arbitrary flash write with that command. Like anyone on Windows can call CV flash update to write to that flash. To be fair, normally you need, everything is encrypted on that flash, so if you don't have the key material for that, that's not doing you very much good. But we just leak the keys, so it's like, okay, now we're getting somewhere. It's like all of that kind of begs the question of like how is the boot process, how secure that boot process is, because really like better diagram as before, that's the boot process. The boot ROM is going to verify the SBI, and the SBI is going to read the fuse key and use that to decrypt the secure code descriptor that contains more keys that are used to populate the execution in place and then start the application firmware. But here, like if you're paying attention, there is no signature check at that point for the application firmware. So the whole security of the application firmware relies on the OTP keys and the secure code descriptor keys being like, not leaked. Otherwise, like if you can leak those keys, you probably can modify the firmware, which is not good. So can we do some firmware modification? So in theory, we can dump the device keys, just showed you how. We can retrieve the SCD content and decrypt it, like we have arbitrary read primitive now. And then, that's why it gets complicated. We could, encrypt and HMAC a blob of data and use CV flash update to overwrite a chunk of the firmware, but you kind of run the risk of like fucking up your device, if you try to reflash the thing that's being executed. So it's like feels like eh. But instead, what we can do is we can forge a new SCD, because it's the same stuff, and put our own RSA key that's used for firmware verification in it. We create a public-private key pair, and we just put the public key in the SCD, and we flash that, and then we forge a firmware update, and that should work. Did it work? No. So what happened is I fucked up and I flashed the wrong SCD with the wrong indebtedness. So it's it was a good idea, but it's the bits were flipped and it just bricked the device. It stopped responding and couldn't do anything. And that's why here I'm trying to recover it by, I was, not cray-cray, so I could make a dump of the valid stuff first, and then I was reflashing the normal thing to fix it. And then I did it again, but I flipped the bit order so that it's in the proper indebtedness, and this time it worked. So nice, this time we can see the device report over the USB that is version string is control pwned, because I'm 12 and I these things. And so yeah, the application firmware was modified, and that's persistent. Even if you install Windows or whatever, that modification will stay, because actually nothing to do with Windows. And that can lead to a permanent implant, which is not great. And so now we talked about the unified secure hub, which is the thing this device, but it's not so secure anymore. So what can we do with that? So there is a fun function called CV fingerprint identify that's used by the system when you try to log in with your fingerprints. Windows Hello is going to say to the device, the fingerprint reader, or control voice in our case, check the finger on the fingerprint reader, does it match any of those, templates that are stored? And the firmware decide yes or no whether they match or not. So could we make it so that it always say, yes, totally, it matches, I swear, that's the proper person, yeah. So what happens here is I modify the firmware, so it just say yes every time. And I have a plastic finger with a piece of green onion taped on it. That's just to make the contact work. And what happened when you press the green onion on the fingerprint and the firmware just say always yes? It works. And you bypass the login screen and you see that the system was spawned. So that's cool, right? But can we do more? Is there more stuff we can do? I was I want to attack Windows now. It's we've seen stuff running a system, the SLR. But before, I just need to give a few context about data encapsulation. And the way data transit between the firmware and the host. So when you send a CV command, the host is going to prepare the arguments, and there is different type of encapsulation. So and it's more decapsulation that makes sense, where it's telling the data you receive is going to be split in different parameters, and that's how it's being defined. For instance, that one, the first one just means the data you're getting is just going to be some raw buffer, and you just copy the data in it. While that one is going to be actually the data is going to be split in two different parameters, the size value and then the buffer. And those are like, encapsulation types, those are like more or less like, I don't know why it's so confusing, it's overcomplicated, I think, but the fun stuff also is when you call the function, the host is going to prepare the arguments, and it's both like from what is going to be sent to the device, but also what you expect to receive from the device, while telling the device, oh, my output buffer is like that size, and I'm expecting that type of data. So the host decides all of that. Then like what happens, like the whole thing gets serialized, sent, like the command is invoked, and upon return it gets deserialized and the data are like split, decapsulated, sent back to the user. Practice that looks like that for like CV get random. You init the parameters, like both sides, the going to the firmware and going back from the firmware. You call here like the CV get random command, and then like the thing that gets decapsulated and sent back to the user. So nice. But on the firmware side, like for like CV get random, you can see that it's redefining the output type. So the decapsulation type is expecting to return, and also the size is going to return. So in our case, we can see the output side is like the input side. So it's like, stuff that should be expected, But the host trusts that new serialization, and it's fine as long as, the firmware like is nice. But we've seen that we can mess with the firmware, and so the question is like, hey, what happened if we change the firmware so that it doesn't return the proper like encapsulation, proper size, like it's not great. And really, like what happened if you do that is like it leads to like overflows, if you send too much data back to the firmware, to the host, and type confusion if you change the decapsulation type. So that's not cool. I mean, it's good, I don't know. But basically what we can do is backdoor the CV get random function, so that if you ask a certain amount of data, like a magic value, instead of returning random data, it will send a malicious payload back meant to exploit that. So let's see how we would do that. We can see during decapsulation on the host, the way it works, like it expects two variables, the size and the data. And you can see the size is just going to be stored as an integer on the stack. And then like, the buffer will be like, filled and returned to the user. So as I said, what we can do is backdoor the command so that if you ask for a specific size, it's going to return like malicious data instead. And the malicious data would just be like changing the decapsulation so that the plen, which is like an integer on the stack, is going to get confused and instead being filled by the data you're sending because it's going to believe it's just like a raw buffer instead. And with that, we can just exploit the CV get random function, and we're going to see how it looks like in practice. So I create like a toy binary on the right side that basically just calls CV get random. If you run it without any command argument, it's just going to call the legitimate function and get the data. If you put a command line argument, it's going to send that magic size to trigger the backdoor, and it's going to get exploited. So let's see how it looks like. So like here I'm just showing, like the vulnerable function is like straight out like calling CV get random. And I'm running it twice so that the first 2 times it's just getting random data, just to show that it actually works. But the third time, I had like a command argument so that it's calling the get random with the backdoor value, and boom, we got a calc because we can exploit Windows this way. So fun, but that was a toy binary. Like I wish there were like a legitimate stuff that was using CV get random, but I couldn't find any. So I was like, let's hunt more. I want to exploit the system service now. Challenge is like we need to find something with a high privilege that use this control vault DLL that doesn't have ASLR, and hopefully in a setup that where like the stack cookie is not going to get in the way. So the targets, like the Broadcom services that we were like seeing before, some third-party application. Unfortunately, I couldn't find any that were being used like recently, or Windows Hello, the thing that deal with the fingerprints that we've seen. So I spent like hours looking over like, all the various like CV commands, the stack. That's me being really sad. It's really exhausting. It's a really annoying process. But eventually, I struck gold, and I found that DLL and that command, which is basically part of the glue code to connect the fingerprint reader to Windows Hello. And so this adapter, like this function, can be called. And what it takes is that it checks if object exists in the firmware. It takes a handle, called like get object, which is a wrapper around CV get object, and we can corrupt CV get object the same way we did like for CV get random, and backdoor it the same way so that if we modify CV get random so that if you ask for a specific handle, it will send malicious data. Here is the object header. Like you can see, it's a stack variable. So if we can overflow that, what it looks like here, it's like somehow it's after the bit, like that's the stack frame of the function, and somehow the object header is after the stack frame. I'm not sure why. But if we look at the parent function, you know, that's where the object is. And if we overflow that, you know, there is no stack cookie here. So if we overflow is off, we can override the return address of that function and, you know, exploit that thing. And so in practice, to reach the whole function I was talking about, the idea is like the DLL from Broadcom is loaded by the Windows biometric service. And it exposes like some kind of a device I/O control, but for those biometric devices. And it also can be called by any regular user. And in practice, what happened is you have that call stack where like a user can call the control unit command for using like biometric APIs on Windows, and would eventually like lead to calling the CV exit CV object, leads to like CV get object, and then we can like exploit all the way up back. And using, as I said, the same idea of we can overflow the object header and corrupt the stack of that function. And the idea is we backdoor CV get object so that it will only do that if you ask for a specific object so that we don't break the whole system by accident. And in practice, that looks like that. At that time, I've already flashed, you know, a malicious firmware that will contain like a payload that once executed will pop NCAT, and this way you can connect to it and get a shell. And on that side, you have the Windows biometric service. And to trigger the exploit, we just use the Windows biometric APIs to request the specific object that trigger the bug. And in practice, it looks like that. So that's the shell command that will be executed by our payload that's built in the malicious firmware. We run the thing that asks for the malicious object. We can see here that just pop like NCAT under like SVC host. And it started like a shell. So we can connect to it. And if you check, where are we? You know, we are running a system. So with that, we are like able to get like a system shell from, you know, having hacked the board. Pretty cool. So what have we done so far? We got code execution on the application firmware. We were like able to modify it permanently. We bypassed the login screen with a green onion. Well, that's nice, and we got also system privilege. That's cool. Can we do more? Is there anything left to do? And there's one thing that was kind of cool. It's like, if you remember, like the board is connected to the motherboard, but it's like technically it's a USB device. And I was like, can you just connect it to an actual, like, to a USB port, you know, so that you could, you know, open a machine and connect it directly? And yes, it turns out you can. That's the setup. Most of the wires are just like 3 volt or 5 volt. And then 2 of the wires are like the data line of the USB thing. And so if you plug it to your USB connector and then plug the other side into a computer, it's going to look like that. So here I'm basically connecting a separate board over USB. And you can see a new device is going to appear that's also a control vault device. And you can see there's 2 of them because that's that laptop that also had one already in it. And then when you run, you know, the CV get version, you can get the version of the board you just plugged in. And so what that really means is that now, like all of the stuff I was talking about, I would like assume, you know, it was like a malicious user or like an exploited user. It turns out we can also do a physical attack and do exactly the same stuff. So if you leave your laptop unattended in your hotel room, you know, and someone has like 10 minutes to like mess with it, you know, they can open the laptop, unplug the ribbon, plug it into malicious attacker machine, and compromise the whole stuff. So as a summary, like what we can do, are the main attack scenarios to see here. So one is post-compromise, like a user like clicked on some malicious stuff, gets popped, and then the threat actor that popped that, you know, could, you know, modify the firmware inside the laptop and use that, you know, to compromise Windows and have like kind of a way to get back into the system, you know, eventually if, you know, they get, you know, erased and, you know, people will install Windows and so on. Or the other angle is like a physical attacker, you know, like someone in your hotel room or, you know, you leave your laptop unattended, to modify the firmware and in that case both bypass the fingerprint reader or, you know, compromise Windows the same way. Pretty cool. So yeah, in practice, results of that, like Dell reported, Dell published an advisory in June. All the reports for those bugs are like released on the Talos website. There's a bunch of CVEs, and there's like a few more coming like in a month or so. And there's 2 technical write-up, like a high-level overview that just show the cute videos, and the technical deep dive where like it's like all of that plus more details. So yeah, so as a conclusion, like yeah, I think firmware security is not a new topic, but I think it's really important. I think it's crazy that we have this kind of devices in our laptops that's been there for like 15 years. It's like completely undocumented. People don't know what it is. And it can reach that level of compromise from that. And I think, as security researcher, we should, either investigate the device in our systems, or if you're like more on the buying side, like maybe you should tell your vendors, oh, we need more transparencies, like what's in it, like how it works, why it's not documented, and we could advocate for more transparency. So yeah, I hope that was interesting. I think I have 5 minutes for questions, and otherwise you can reach out like at the bar or like on Twitter. Thank you.
So we have time for 2 short questions.
Thank you. So one of the many questions I have for you is that at one time during the presentation you showed that you guys found the type confusion in the firmware, right? Did you find any specific class that would allow you to be able to exploit the type confusion?
Oh yeah, so for exploiting type confusion is actually like the process I use to exploit the CV get random, and I can't remember if that was the case also for the CV get object, but in the CV get random case, when data is being decapsulated, like the first parameter is assumed to be like the size of the data, and that's just like an integer that is being stored on the stack.
Okay.
But I changed to exploit that, I changed the encapsulation type to be like, oh, the first parameters is not like an integer and it's not the size, it's straight out the data I'm sending back to you. So by modifying that encapsulation, I can overflow that stack variable with arbitrary data.
Okay. Can
Makes
I ask
sense?
more questions? Okay, yeah.
To reflash the firmware on the device, did the drivers restrict that access to just administrators, or were you able to do that without the privesc?
Any low privilege user, like the only thing you cannot do is like if you're in a sandbox context, but non-admin user can do that, yes.
Wow.
Yeah, right. It's like the whole API is open to anyone.
So let's thank him for this very elaborate work and great talk.
Thank you.
And give him a warm round of applause.
Thank you.